Okay, guys. So I'm just going to go through the notes here just like I would if I were in class anyway. Just kind of continuing up where we left off last time. Um, Let me see. So last time I think we talked about this theorem here. Again, we can't just memorize everything. We just gotta remember that. Yeah, what does it mean? Limit an plus bn equals this guy. We have to know, what that means. I think I covered this one last time, so maybe I won't slow down too much here. Triangle inequality, of course. Let's see. Yeah, obviously, upper bounds and lower bounds were important to us. Let's see. What was some important things here. Let's see. So this is the proof of the product of sequences, the product a and b n. That limit was L times M. Yeah, this one is a little tricky, right? Yeah, this is definitely a little tricky. I would put this in the hard category. You have these multiple steps here. Um, let me see. We got these A n B n minus LM. I mean, ultimately, we want to show that this guy is less than epsilon. Yeah, but to do that, that was quite a bit of work. Had multiple steps, and some cleverness to it. Had to make use of the fact that a convergent sequence was bounded. And then, of course, had to make the fact that both sequences converged. Yeah, this would be in the hard category for me. It's at these multiple steps. Um, there's just kind of a lot going on here. Had to pick some clever epsilons. Ultimately, we wanted to get that thing was less than epsilon. Yeah, that's a hard one. There's a lot kind of going on there. Okay. Let me see here. Limit comparison. Um, wasn't perhaps the most important thing for us. Again, probably my bullet point going into it is, suppose the contrary, L is greater than M, so set epsilon to be L minus M. Um, yeah. Yeah, if A n is less than B n, first at some starting point, we would say L is less than M. I mean, we gotta have epsilon. I mean, and then try to figure out these details, try to use triangle inequality and so forth. This is a little tricky. Maybe that's like a medium one for me, like a medium with choices. We had to show that this A sub capital N was greater than B sub capital N. So this might be like a medium with choices. It's kind of tough. Okay. Let me see. We just had some little silly facts, useful things, but not too important about bounded sequences. Oh, by the way, I'm going through that master file I have now of all the notes put together in one big PDF. I've been going through that here. If you want to follow along with me, but obviously skipping some things. Let's see. Yeah, the squeeze theorem. This is kind of like famous mathematics, kind of classical stuff here. Um, I wouldn't just force you to prove the squeeze theorem. I mean, it would be it would be a choices problem, but nonetheless, this might be a good one. Um, yeah, if A n converges to L, C n converges to L, then the middle guy has to converge to L too. A nice theorem. I don't know, not too bad. Maybe like a medium level. Again, I'd probably call it medium with choices, but yeah, classic mathematics. That's a nice result. Yeah, can you figure out these details? Um, yeah, you got to use the fact that A n converges and C n converges, obviously, and be able to try to figure out these details here. This is probably be my big bullet point line if I was thinking about. Let me go into it with kind of one idea in mind. That'd probably be it right there. Um, okay, let's see. When does a sequence converge? This is kind of an important thing. Monotone sequences, I mean, kind of is straightforward, right? Increasing, decreasing, important definitions. Yeah, monotone convergence theorem, love it. Yeah, I mean, this named theorem, famous theorem. Um, yeah, if it's an increasing sequence that's bounded above, it must converge. Yeah, this is nice. This is kind of like important stuff for us. Yeah, we considered the set of terms, and the least upper bound of that set was what the sequence converged to. Nice result. It makes use of a lot of things we've considered in this class. Um, yeah, definitely like a medium one with choices. I would say a little tough. A lot kind of going on here. Yeah, monotone convergence theorem is a good one though. Yeah, maybe like a medium problem with a choice. It is a little tricky. Yeah, you had to make use of that old fact we had a long time ago. Yeah, since L is the least upper bound, that means there exists something in the set such that L minus epsilon is less than X. There's kind of a lot going on here. There's kind of a lot going on here. There'll definitely be some. This could be definitely a choices problem to try to figure out that AN converges to this L. That's a little tough. But I like it though. Monotone convergence theorem and classic sort of stuff. Let's see. Subsequences. We did some things with subsequences. Um, if a sequence converges to L, then every subsequence converges to L. I mean, not that important to us, right? I mean, sort of. Um, not the most important thing in the world. Um, yeah, now obviously Bolzano wire stress is quite, yeah, was important for us, and you guys know as much as we joke about wire stress, he is one of these titans of real analysis, so I'd be happy to have him on the exam here. Yeah, every bounded sequence contains a convergent subsequence. Um, Once again, though, this proof was just too hard. It was like the hardest thing we've done in this class. So once again, just like I had on that quiz a while back, I would not ask you to prove the whole theorem, but rather just tell me. Yeah, so every bounded sequence contains a convergent subsequence. Tell me what the subsequence is and what it converges to. Explain to me how you would find the subsequence and how you would find its limit. You don't have to actually prove that that subsequence converges to that limit, but just tell me what it would be. In other words, it's kind of like the first 75% of the proof. Um, yeah, you start this bounded sequence. Had to make use of this. Had to make use of this nested intervals theorem to get this limit. So explain all this process to me. Where did these intervals come from? That all of that. Yeah. Now to find the subsequence again, you go back to the intervals to get your subsequence. Just sort of explain this process to me. Um, so in the notes it says repeat indefinitely to get a subsequence AIN. We claim the limit of AIN equals L, and you can just stop right here. You can just stop right here. So just describe where the limit comes from and where the subsequence comes from, and you can just stop right here. You don't have to actually prove that the subsequence converges to this L. Okay, so it's like the first three quarters of the proof. So we can skip this part of the actual proof here. It's just too much. Cauchy sequences, yeah. I mean Cauchy again, another titan of real analysis, right? Great result here. A sequence is a Cauchy sequence if and only if it is convergent. I like the Cauchy definition. I mean it's a kind of an important definition. Um, yeah, the terms of the sequence have to be getting close to each other. Um, yeah, nice definition. Great theorem here. I mean, fantastic theorem. So one direction was a lot harder than the other, though. So if we're trying to prove, let's see. So a sequence is a Cauchy sequence if and only if it is convergent. So, okay, one direction was definitely harder than the other. So going in the forward direction, if you assume that AN is a Cauchy sequence and you will prove that it's convergent, that's a hard one for me. This direction is hard. Um, yeah, this direction would be a hard proof. Yeah, you have to first first you have to prove that it's bounded, and then you use Bolzano-Weierstrass and get the subsequence and the limit, and then prove that it converges to that limit. This was tough. This was tough. This would definitely be a hard one for me. The other direction would be a medium problem for me. So if I just said to you, prove that a convergent sequence is a Cauchy sequence, then that's it. Just the one direction. Prove that a convergent sequence is a Cauchy sequence. That's a medium for me. That's a medium for me. Prove that a Cauchy sequence is convergent. That's a hard one for me. That would be a hard proof. Okay. Um, yeah, that would be a hard proof. So anyway, okay, okay, but yeah, good theorem though. Anyway, um, all right, let's see series. Yeah, definitely. We spent some time doing series stuff. Um, let's see here. Yeah, once again, I do like these, similar problems like you had in the quiz recently. Show me whether or not this series converges or diverges. Um, those are good problems. You got to try to use your tests. Um, Let me see. We had some, yeah. See something like this, something like this though. This sum. Hopefully that would just be easy just to kind of figure out on the spot, so to speak. You consider the partial sum sequence for the A sequence and the partial sum sequence for the B sequence, and that shouldn't be too hard to show these add up accordingly. Um, Cauchy convergence criterion, great statement. I mean, just a great statement. Converges if and only if. Yeah, the series converges if and only if Sn minus Sm is less than epsilon. Great statement. Um, Great statement. Not a bad proof either. If you do this if and only if business, this wasn't too bad. Yeah, really not bad at all. Really not too bad at all. That's a nice one. Yeah, that's a nice one there. Not too bad. Let's see. Convergence test. Yeah, again, we want to be able to use our convergence tests. We don't necessarily have to prove every single one of them. Um, yeah, make sure we can use our convergence tests, p-test, and alternating series tests. Yeah, just to try to figure out how does something converge, diverge. Comparison test was obviously important. Limit comparison test is also nice. Ratio test is also a good one. We don't really see it that much, but um, let's see. Proof of the divergence theorem. I do kind of like this. Yeah, proof of the divergence theorem. Yeah, prove that if the series converges, then the limit must be zero. Yeah, kind of a cutesy little proof. Yeah, this limit of an is the same thing as an plus one, but that's just Sn plus one minus Sn, but converges to the same S, so it must be zero. That's cute. That's cute. That's a nice proof. Not too bad. Comparison. Proof of the comparison test. This is maybe like a medium one. There's just kind of a few things going on here. Yeah. So we assume that the B series converges and prove that the A1 converges. Yeah. If you use the Cauchy criterion, it's not too bad. Not too bad. It's like a medium one for me. No topology on the final exam. Don't get me wrong, having a limit point. So for example, when we talked about like limit points, yeah, limit point is an important consideration when we talked about the limit of a function or derivatives or these sorts of things. Yeah, limit point was an important consideration. Um, so in particular, if I ask you to give me the definition for the limit of a function, yeah, you want to include, so say x approaches c, you want to include the fact that c is a limit point. You need to state that. However, I am not explicitly going to ask you for the definition of limit point by itself. And I'm not going to ask you for the definition of epsilon neighborhood, okay? Um, again, we use these things, but I'm not going to test you on them on the final exam, okay? So I really wouldn't even study that topology stuff. I'm much more interested in this. Yeah, the limit of a function. Obviously, very important definition. Here, we want to just write down C is a limit point of our domain. Yeah, it's important here, but otherwise, that's all we wrote. That's all where we really care about it. Um, okay, okay. So again, yeah, limit of a function. I would, in my mind, I would. It's probably best to try to relate this back to sequences. For every epsilon, there exists capital N. Now we say for every epsilon, there exists delta, right? And right before we said the sequence was getting close to the limit. Now we're saying the function is getting close to the limit, right? Um, so there's just those parallels there that I think can help us keep this straight. And do we consider this for every single x value? No, only for those x values that are close to c. Um, yeah. So anyway, I think the sequence definition of converging sequence is helpful. But this is obviously a very important definition. This was like the bedrock of Calc 1, right? So yeah, obviously this is something very, very important. Definitely expect that definition. Let's see. Oops, looks like I have a duplicate page in my notes. I told you I might. Let's see. Uniqueness of limits. Um, yeah, we just sort of mention these facts and use them to help us, yeah, compute some things. Don't want to slow down too much here. Let's see. Yeah, now much more important. Much more important. Continuous function, of course. Super duper important. Yeah, we love continuous functions. We love differentiable functions. Yeah, both very important definitions. The continuous function definition obviously is super duper similar to the limit definition. The only difference is, I mean, basically the only difference is instead of capital L, you have f of c. I mean, that's it. I mean that's pretty much it. Um, so really, it's not like you want to think of these two definitions as just completely different things that require complete separate files of memory in your brain. I mean, no, they're kind of like the same thing, right? So definitely want to sort of keep that in mind here. Let's see. Let's see. Let's see. We had some facts. Yeah, as I mentioned in class a long time ago, I'll repeat here though. Yeah, extreme value theorem and intermediate value theorem. These are classic results. I like these results. I yeah, we didn't prove them or anything, but I just would like to see if this was on the exam. I would just like to see could you recreate some of these details? So, for example, if I said to you, let f be a continuous function on this closed interval ab, um, then there exists C and D in the interval such that what? Could you tell me? Could you finish off the rest? Yeah, there exists C and D such that what? What can you say? Well, I mean, it's the extreme value theorem, right? So basically, there exist extreme values. There exist points like f of c and f of d that serve as extreme values, upper bound and lower bound, for the entire function. I mean, again, extreme value theorem. There exist extreme values. So, could you figure out what that means? That's kind of the idea here. Um, so again, I would just sort of just can you give me the conclusion of the theorem? I give you the top half here. Can you give me the bottom half? Um, Similarly with intermediate value theorem, I would tell you that I have a continuous function on AB, um, and suppose that y is some real number such that y is between f of a and f of b, or y is between f of b and f of a. Okay, so I would give you all this. Yeah, I have the continuous function, I have this number y. Can you give me the punchline? Can you give me the conclusion? Well, again, it's the intermediate value theorem. Every single intermediate value has something mapping to it. Yeah, so I would want you to give me this conclusion here. Then there exists x in the domain such that f of x equals y. Yeah, every intermediate value has something mapping to it. Yeah, it's the intermediate value theorem. Um, so again, I would give you the top bit here, and I would just want you to give me the conclusion. Then there exists x in the domain such that f of x equals y. Okay? Okay. Right. Yeah, and of course, derivatives, obviously a super duper important definition. Um, yeah, obviously a very, very important definition that this limit has to exist. Yeah, and of course, as you guys know, this is a big theorem for me. If a function is differentiable at a, then it is continuous at a. And once again, yeah, if this is on the exam, there's no choice. You just got to do it. The other one is that the real numbers are uncountable. If that one or this one, or both, are on the exam, then there will be no choice. Even though both are kind of like medium level proofs, there would just be no choice here. I feel like these are just very important facts to the course. Yeah, really classic, important mathematics here. Um, yeah, and of course, here, the big bullet point is consider this weird thing. Consider this weird thing. We want to, yeah, consider this weird limit. Yeah. I mean, on the left, this just looks like the derivative, but we multiply it by x minus a. That's the big idea. That's the bullet point you really got to have going into it. Yeah, if you know you're working with this guy, try to figure out the rest of these details. Yeah, on the one hand, it's just the derivative times x minus a, the limit of x minus a, so it's just the derivative times 0. On the other hand, x is different from a, x is always different from our limit point, so therefore we could say that these x minus a's cancel, and we just have a limit of f of x minus f of a, and therefore it follows the limit of f of x is just f of a, so it's continuous at a. Okay, but again, obviously this was kind of the big idea. You have to have this this somewhat strange consideration in mind, I would say. Yeah, so definitely make sure you're comfortable with that one. Yeah, classic stuff there. What else? We had a couple of facts here. Um, Proof of product rule is I would think of this as kind of like a hard one. With all if you really do it properly, right? I would think this is kind of like a hard one. Um, yeah, I mean, first of all, you had this weird consideration minus f of a g of x plus f of a g of x, and did some clever factoring and stuff. A little tricky there. A little tricky there. Um, but I really want to see some of this philosophical understanding, though. Yeah, you have the limit of some big ass function. How do you know that you can distribute this limit, so to speak? How do you know you can think of this as limit of this times the limit of this plus the limit of this times the limit of this? How do you know you can distribute that limit? I mean, well, it's because f is differentiable. Therefore, by definition, the limit of this guy on the left here exists. Um, okay. Also, since g is differentiable at a, we know it's continuous at a. So the limit of g of x is g of a, and in particular, the limit exists. It converges to something. Um, yeah, same sort of story on the right. We need this analysis. That's how we know that we can really properly distribute this limit here. Okay. So in light of all that analysis, I probably would put this in the hard category, um, especially since we just did it recently too. But anyway, I will be looking for this philosophy here. Okay. Yeah, because in Calc 1, those students just mindlessly distribute the limit without even thinking about it. But you guys in 347 have got to think about it, right? This is kind of the whole idea of the class, quite frankly. Um, See, quotient rule is definitely a hard one for me. There's kind of a lot of moving pieces here, right? We had to use the product rule, we had to use the chain rule, we had to set up these auxiliary functions before we even began. This is kind of a hard one for me. It's kind of a lot of, I don't know. It's not too bad, I guess, but there's just kind of some a lot of pieces, and we just have to be very careful with how we go about our analysis here. That was a little bit tough. Oh, by the way, I wrote down the proof of the power rule. It's not going to be on the exam. I wrote it down in my notes just for completeness or whatever. But this will not be on the exam. The power rule will not be there. It was fun to do that with you guys in class. Yeah, that will not be on the final exam. Okay. Um. Okay. I guess that's it. I guess that's it. That's certainly enough, right? I guess that's it. Of course, please email me if you have any questions. Also, too, we can set up appointments, perhaps on Zoom or in person as necessary. But yeah, well, let's keep in touch, guys, and good luck with all your other exams.